If you held tens of billions of dollars in your hands and plan to build the most powerful giant rocket in human history to send humans to Mars, what materials would you use to build it? Intuition tells us it must be the most advanced carbon fiber composite material on Earth, or that incredibly lightweight titanium alloy used on airplanes, right? After all, in aerospace, lightness is life. However, Elon Musk, known as the real-life Iron Man, in SpaceX's most critical Starship project, made a decision that made jaws drop across the entire aerospace industry. He abandoned the carbon fiber plan that was halfway developed, and for which even the molds had been purchased, turned to a steel mill and said, "Give me a pile of the most ordinary, most down-to-earth stainless steel." That's right, it's the 300 series stainless steel. Similar to the materials of the soup pots and sinks in your kitchen. Many people thought Musk was crazy when they first heard this, thinking he had gone mad trying to save money. Some even mocked that this wasn't a rocket, but a giant silver soda can. But if you really think this is just to save money, then you are underestimating these crazy engineers. In today's episode, let's break down why this decision, which seems like a step backwards, is actually the most brilliant engineering stroke in SpaceX's journey to Mars, and the astonishing logic of material science and durability hidden behind it. We have to talk about why everyone initially thought stainless steel was a joke. In rocket engineering, there is an insurmountable iron rule called the gravity penalty. For every extra kilogram of weight you add to the rocket, you have to consume more fuel to push it. And to push that extra fuel, you need to add even more structural strength. This is a vicious cycle. So, for the past half-century, the mainstream in aerospace has been pursuing extreme lightweighting. Carbon fiber is the darling of this era with its extremely high specific strength. It weighs only 1/5 of steel, but is stronger. SpaceX certainly thought so in the beginning. They even commissioned the world's largest carbon fiber molding at the port of Los Angeles. But here's the problem. The rocket doesn't just need to go up. Starship has an even crazier goal. It needs to be 100% recoverable and reusable as quickly as an airplane. When you consider reusability and extreme environments, carbon fiber's flaws start to emerge like a nightmare. First is the temperature. When a rocket ray enters the atmosphere from space, the fuselage surface generates temperatures exceeding 1,000 degrees due to intense friction. Carbon fiber is a very delicate material. It requires a lot of resin to bind, and these resins start to soften or even decompose at around 200 degrees. This means if you build a rocket with carbon fiber, you must apply a layer of very thick, very heavy, and very fragile heat shield tiles on the outside. If just one tile falls off, the carbon fiber structure inside will burn through like paper. The tragedy of the space shuttle Columbia. It was due to the failure of the thermal protection system. Next, let's look at why Musk chose stainless steel. Specifically, 301 stainless steel. This stuff is indeed much heavier than carbon fiber at room temperature, and its performance is mediocre. But the magic happens at two extremes: extreme cryogenic cold and extreme heat. What's inside the rocket's belly? It's minus 183 degrees liquid oxygen and minus 160 degrees liquid methane. Most materials, including carbon fiber and aluminum lithium alloys, become as brittle as glass at these low temperatures, shattering with a light bump. But 301 stainless steel has a strange temperament. Its strength actually explodes at low temperatures. At room temperature, its strength might be average, but at liquid nitrogen temperatures, its toughness and strength increased by 50 to 100%. This means that when fully loaded with fuel, the stainless steel rocket is actually very robust, and there is no risk of cryogenic brittle fractures. Now let's look at high temperatures. The melting point of stainless steel is close to 1,400 degrees, which means at high temperatures of 800 to 900 degrees, it can still maintain a certain structural strength. This is a huge turning point because stainless steel is heat-resistant enough. Starship doesn't need heat shield tiles on the leeward side, and even the tiles on the windward side can be made very thin. In contrast, carbon fiber rockets need heavy insulation layers. Although the stainless steel rocket has heavy skin, the clothes it wears are light. Add and subtract the two, and the weight of the entire system ends up being almost the same, not to mention the cost. This is what makes other aerospace companies break down the most. The cost of 1 kilogram of carbon fiber is about $130 to $150. With a high scrap rate and incredibly tedious processing procedures, it needs to be baked in a huge autoclave for several days. And stainless steel? 1 kilogram costs only $3 to $5. You can find any welder on the street, and if their skills are good enough, they can weld a rocket for you. Musk once joked that at the base in Boca Chica, Texas, they weld rockets like they are camping outdoors. It doesn't matter if the wind blows sand in. This is simply unimaginable in the clean room environment of carbon fiber. This cheapness brings more than just saving money. It brings the ability to repeatedly trial and error. If it costs $1 billion to build a rocket, you will go bankrupt if you fail once.